have an example of what could be in our future that comes from our deep past. It turns out there are events in Earth's history that bear more than a passing resemblance to models of our potential future, particularly if we do not try to contain fossil fuel-driven global change. The Paleocene-Eocene thermal maximum, also known as the PETM, is an event 56 million years ago, and it's a poster child for the climate and ecological effects of natural greenhouse gas release. The PETM lasted about 200,000 years and warmed the Earth by 5 to 7 degrees centigrade. Just how fast the PETM unfolded is still debated, but the evidence looks more and more like an event that developed over a few thousand years, or possibly less. It turns out to be pretty hard to be certain of the date, since most of our archives do not have the resolution to see an event lasting only a few hundred years, like our current spate of global change. The carbon isotope change is consistent with remobilization of greenhouse gases from organic material, so the PETM is similar in that respect to the modern, in being driven by the release of copious amounts of previously buried organic matter, in our case by burning fossil fuels, and in the case of the PETM by another mechanism that I will get to presently. A natural question about our own time is whether we'll trigger a wave of extinctions thanks to our use of fossil fuels. Here the PETM offers some reassurance on this point. There was notably little extinction of surface ocean plankton or terrestrial biota during the PETM. Still, species did move around quite a bit. For instance, there are migrations of both ocean plankton and iconic animals like the first horses. The horses, for example, seem to have used the PETM to move from China to North America across Greenland. The horse migration worked because Greenland was almost certainly green then, with extensive coal-forming forests all around the Arctic Circle. To be sure, not everybody made it through the PETM. For example, there was a notable extinction of benthic foraminifera in the deep sea. The survivors were species that could handle low oxygen environments. The implication is that species that needed well-oxygenated conditions particularly suffered, perhaps because ocean oxygenation was depleted by elevated organic matter production, or by the reduction in the oxygen holding capacity of water as the ocean warmed. Notably, other than benthic foraminifera, the PETM is not associated with a wave of extinction as some have predicted for our future. This is not to let us off the hook, of course, since we are causing extinctions in other ways, such as by overexploitation and by habitat destruction. But these things are not primarily the fault of PETM-style global change. It is surprising that there is not more extinction associated with the PETM. We note, for example, that measurements of boron isotopes and boron-calcium ratios show that the surface ocean did actually become acidified. In addition, acids, mainly CO2 dissolved in the ocean, extensively reacted with carbonate ooze all across the ocean floor. Hence, the PETM is marked in many places in the oceans by a red layer, where red dust and clay has been concentrated by carbonate dissolution. This clay layer is a very distinctive part of the PETM's record and is instantly recognizable to anyone with some experience, since Paleocene and Eocene sediments are typically white or tan thanks to their abundance of calcium carbonate. The greenhouse gases that cause the PETM warming and ocean acidification also affected terrestrial weathering processes. Warming increased rainfall, flooding, and weathering. These processes produce deeply weathered soils, increased clay deposition in the oceans, and changes in osmium isotope ratios in the deep sea, reflecting a global increase in weathering of shale on land. The twin increases in terrestrial weathering and dissolving deep-sea carbonates are what ultimately ended the PETM by absorbing the released greenhouse gases over around 150,000 years. That 150,000-year time period is identical with models of how long CO2 remains cycling through the biosphere before being buried in sediments and rock. Hence, the whole PETM has the fingerprints of a greenhouse gas fueled event, very much like our experiment in burning fossil fuels. So, what was the source of those greenhouse gases, and what natural process, as opposed to us, could produce such rapid global change? The PETM was first identified because of the benthic foraminifera extinction. Pretty quickly, the suggestion was made that the cause was the melting of gas hydrates, a frozen form of water within deep-sea sediments that traps CO2 and methane. If the hydrates were melted, the theory went, the methane would escape from the seafloor and produce rapid and substantial greenhouse warming as well as ocean acidification, along with all the other signatures of greenhouse environmental change, like intense weathering, elevated rainfall, species migrations, and of course that benthic foraminifer extinction. However, the gloss came off the hydrate theory when it was found that much more carbonate had been dissolved in the ocean than could be accounted for by the amount of methane that would produce this 4 to 7 degree centigrade change in global warming. The amount of surface ocean acidification also suggested that much more greenhouse gas than methane hydrates could supply was involved. Instead, the models and data now suggest that ordinary organic matter mixed with volcanic-derived CO2 could explain the features of the PETM. That recognition led to the revival of an idea, considered a bit fringe at first, that volcanic eruptions offshore Norway and Greenland had literally baked buried organic matter, causing eruptions of CO2 from the seabed. There is physical evidence for this idea in the form of giant explosion pits of PETM age in Norwegian sediments. High precision dating of volcanic intrusions in Greenland also points towards magma emplacement at the same time. At this point, I think that most of my colleagues agree that this combination of magmatism and volcanic gas eruptions produced the PETM. Now, you may recall that this new model for the PETM sounds quite a bit like the growing consensus that the Permo-Triassic extinction was produced by the Siberian Traps volcanic eruptions that intruded into coal deposits. I confess that I was initially skeptical of this mechanism for both events because of the problem of how volcanism could produce an abrupt, global-scale climate event that's really fast. The PETM, for instance, sure looks like it went through the full scale of global warming in perhaps only a few thousand years. How does even a big eruption release that much gas that quickly? Here it is important to avoid thinking of the PETM or the Permo-Triassic extinction as a single cause event owed completely to a volcanic trigger. Perhaps the eruption set in motion the dissolution of gas hydrates or increased the weathering rate of those Arctic coal deposits. Indeed, this idea that there are various parts of the climate system that could be flipped into a new state that reinforces global change is one of the big worries we have today. Our use of fossil fuels is producing warming that is already being amplified by fires burning in peat deposits in Siberia and by melting permafrost that holds methane hydrates. An increasingly ice-free Arctic Ocean is expected to start absorbing more and more heat in the summer, which will change weather systems and make it harder to freeze the ocean in the wintertime. In short, one big worry about global change that we're starting is that we will set in motion environmental change that we cannot stop, even if we finally stop using fossil fuels. The PETM and the Permo-Triassic events probably both had similar feedbacks at work, that once set in motion essentially ran away in a cascade of massive environmental change. So, in summary, the PETM is simultaneously comforting and a stark warning for our future. It is comforting in that there is remarkably little extinction, other than those poor benthic foraminifera, despite the substantial migrations of many species that were set in play by global warming. Species turn out to be pretty resilient after all. The PETM is also a warning, of course, that a dam burst of change can be set in motion that greatly exceeds the force of the original trigger. In the context of this lecture, the PETM points to there being many ways that our own impacts on Earth's environment will be visible into the distant future. If we do not manage to contain our fossil fuel use, we are likely to reproduce many of the things that happened during the PETM, including a whopping carbon isotope signal, extensive dissolution of carbonates and surface ocean acidification, deep weathering, and a hotter, much more flood-prone climate, as well as species migrations that will be visible for many millions of years.